In 1855, the grand halls of Paris housed a heavy brass pendulum suspended from the ceiling. Leon Foucault had built it to demonstrate the steady, unstoppable rotation of the Earth. It stood as a monument to continuous motion. But away from the bustling Parisian streets, Foucault was running a very different experiment at his desk. He was trying to figure out how to force continuous motion to stop. He placed a flat, circular copper disc on his desk. Because copper isn't magnetic, it doesn't attract iron. Then he took a bar magnet and began rapid spinning it just above the disc's surface. Even though copper is non-magnetic, the disc begins to spin along with the magnet. The changing magnetic field induces electrical currents inside the material, turning the metal into a natural electromagnet that generates its own magnetic flux to fight the external movement. Foucault had isolated swirling, spiral-shaped loops of induced energy. Today, we call them eddy currents. He had uncovered a physical paradox, an invisible, frictionless electromagnetic force whose sole purpose in nature is to resist change. The challenge for the next generation of engineers was figuring out how to harness a force that only wants to slow things down. Half a century later, heavy-duty vehicles were hauling immense loads of steel and cargo. When an engine like this vintage Union Pacific model heads down a steep mountain pass, it builds up millions of pounds of kinetic energy. Stopping that kind of mass with traditional mechanical brakes is dangerous. The sheer physical contact required at those speeds causes brake pads and drums to warp, wear down rapidly, and eventually fail. To solve this, engineers built the eddy current brake. They mounted electromagnets closely around a metal drum attached to the train's spinning axle, hovering just millimeters away from the surface. When those electromagnets fire, they hit the spinning drum with a massive, sudden change in magnetic flux. The metal reacts instantly. It spawns dense eddy currents that fiercely fight the rotation, dragging the axle to a halt without a single point of physical contact. By weaponizing nature's resistance, engineers achieved frictionless stopping power. But according to the law of conservation of energy, energy cannot be destroyed. So where exactly does all that vanished kinetic energy go? The kinetic energy is converted directly into what is known as Joule heat. This heat is the result of the electrical resistance encountered by those swirling currents as they move through the metal. Engineers didn't need a moving train to create this heat. They could trigger it artificially by bombarding a stationary metal object with high-frequency alternating current. This is the mechanism driving an induction heating cooker. Coils hidden inside the base blast high-frequency magnetic fluctuations upward into an electroconductive iron pot. The iron pot fights this magnetic bombardment by spawning localized eddy currents. As those currents swirl through the metal, Joule heating takes over, causing the pot itself to become the heat source. These currents connect the physical forces of motion and magnetism directly to the generation of heat. They allow a train to stop and a meal to cook, using the same principle of resistance. But the exact same heat that cooks our food is a severe liability for modern electronics. Left unchecked, that Joule heating threatens to melt down power transformers and destabilize the electrical grids that run the digital world. Transformers rely on changing magnetic flux to move electricity. By design, that continuous change in the magnetic field accidentally spawns massive, unwanted eddy currents inside of their metal cores. This line graph maps operating frequency against heat loss. Notice how the curve rockets violently upward into the danger zone. Because eddy current loss is proportional to the square of the frequency, pushing modern electronics to higher and higher frequencies causes the heat generation to multiply exponentially. The traditional physical countermeasure was to slice the transformer's core into stacked layers of thin silicon steel. This physically interrupted the large swirling loops, forcing the current into tiny, isolated pockets. But at the extreme frequencies used by today's devices, physically slicing the metal is no longer enough to stop the overwhelming heat generation. The solution required a transition from mechanical engineering to chemistry. The answer is ferrite, a unique polycrystalline iron oxide material engineered specifically to fight back. Ferrite possesses exceptionally high electrical resistance. It physically chokes off the ability of the eddy currents to swirl at all, while still allowing the critical magnetic flux to pass through safely. Managing eddy currents is a constant balancing act. By learning to trigger this resistance for power and suppress it for precision, we've integrated Leon Foucault's 19th century discovery into the infrastructure of the 21st.